In this video, we'll cover the problem evaluate division. There's quite a bit going on here in terms of input, so I'm going to try to break this down. For now, let's ignore queries and let's focus on equations and values. So here we're given a series of equations and their values. So each of the indices of these arrays correspond. So index 0 contains this array that has a and b, and index 0 here is 2. This is telling us that a divided by b equals 2. Similarly, this is telling us that b divided by c equals 3. Using these statements, these are kind of statements of fact. They're telling us that this is true. And using that information, we want to figure out all of these queries here. So for example, this one is asking us, what is a over c? Well, we know mathematically a over b times b over c equals a over c, because we know that the b's are going to cancel out with each other. So we can multiply these two values. 2 times 3 is equal to a over b times b over c, which equals 6. And I can quickly model that out. This is a little preview of what we'll do in a second. But we can say, a over b times b over c equals a over c, because these are going to cancel out. So we know that a over b is 2, b over c is 3, so a over c equals 6. And so you can see the answer here is for a over c, the answer we should be outputting is 6. Similarly, we want to compute b over a. We know a over b is 2, so we're just computing we want to flip these two. So that's going to be 1 over what we had before. So it's going to be 1 over 2, which is 0.5, and that is correct. Next, we have a over e, but e is not even in anything that we've been told. There's no definition for e or a relationship with anything else. So we say -1. We say, I cannot compute whatever the answer is here. Like they're saying, no answer can be determined. For a over a, we know that anything divided by itself is 1. And for x over x, well, x doesn't exist. So again, we cannot compute what that is. Okay, so if we look at this problem, we see a bunch of nodes, or kind of pieces of data, and relationships between these pieces of data. So that makes me think of a graph. We have nodes in our graph, which are these variables. And then we have the edges, which show like, hey, a and b are related in this way. But note that the direction matters, right? A over b is different from b over a. So what we can do is we have a directed graph. But there's always, if there's an edge from a to b, then there's certainly an edge from b to a. It just kind of has a different value associated with it. So let's try to take a look at that. So that is what we have this graph modeled out for here. So one thing we know is we know that a divided by b equals 2, and b divided by c equals 3. So you'll notice I'm defining an edge so that if there's an edge from one node, we'll call it x, to another node y, then that defines the answer for x divided by y. We have numbers associated with the edges, and these are going to be weights in our graph. So the edge from a to b has a weight of 2, meaning that a divided by b equals 2. One thing we know is that the reverse direction is always going to be 1 over what we had. So if we had a over b equals 2, well, we can do 1 divided by both sides. 1 over a over b equals 1 over 2, and this actually equals b over a. The left-hand side equals b over a, which is 1 over 2. And so we can compute the left, or I guess not the left-hand side, but the reverse direction for both of our equations. Here it's going to be 1 divided by 2. Here it's going to be 1 divided by 3. Now, the first query we were asked to compute was a over c. So we can write that here. And remember, the way we do that, or at least the way we did it here, was we did a over b, a divided by b times b divided by c. In our graph, that meant we started at a, then we went to b here, and then we went, oops, that's not what I wanted to happen. We started at a, we went here to b, or I guess I'll follow the edge that we actually took, went here to b, then we went here to c. And what you can notice we're doing is we're basically just finding a path from a to c. Because if we have a path, it would be like a divided by something and then it would be, that something divided by some other something, and then that something divided by another something, and this kind of continuously goes on until we're going from something to C. So it's going to be question mark over C. Now I should actually mention all these question marks are different, or like these two are the same. These are both question mark 1, these are question mark 2, these are question mark 3, but these all are going to cancel out. These will cancel out, these will cancel out, these will cancel out, and we get A over C. So if we find a path from our start node A to our end node C, then we have found the answer. We can just multiply all of the weights. So the weight here could be, 5. The weight here could be 2. The weight here could be 3. The weight here could be 1. So our answer would be 5 times 2 times 3, which is 30. As just a random example. The key is that if we model the graph the way we've done it, we just want to find a directed path from our current node to the desired target node. And we're just going to multiply the products as we go. Okay, conceptually that's what the algorithm is going to be. We are going to solve this problem using a depth first search. So we're going to start at, or I guess if we focus on A over C, we're going to start at A, and we're going to do a depth first search and see if we can ever hit C. And we're going to do this for every single one of our queries. So let's see how that looks. I'm not going to erase this because it's going to erase the entire A. But I think we're good to go ahead and switch to code. So we'll come here, and we're going to switch our function to be an ES6 arrow function. First thing we want to do is we're going to try to build a graph here. And remember, this is a weighted graph, so it's going to be a little bit more involved than our typical graph construction. We're going to have our equations and our values, and we don't need the queries to build the graph. Okay, so we'll come here. We'll take in, let's see, can we make this generic? Not really. I mean, we could maybe like edges and weights. We could name it generically like that, but it does seem pretty unique to this problem. So I'm going to write a build graph function that is unique to this problem. So we'll have our graph, which is going to be an object as always. We'll return it in the end. We'll iterate. We're actually going to need to access both of these arrays. So I'm just going to have indices. We'll do I equals 0, I is less than, equations dot length, I plus equals 1. And we know equations dot length must equal values dot length. I'm sure that's given down here. Yeah, here. They must be equal. So it doesn't actually matter whether or not we use equations or values here. Now, I'm going to get our equations. So we have the numerator and we have the denominator. Should we use those names, or should we use dividend and divisor? Graph at dividend at divisor. Graph at numerator at denominator. Oh, touch on. I don't know what that means. Okay. I guess we can, let's see. Let's go with numerator and denominator. So numerator and denominator is equal to equations at I. You know what, maybe let's go with dividend and divisor. Because, yeah, I guess that has more significance to what we're actually doing, which is dividing things. So dividend means the thing on the top of the fraction. Divisor means the thing on the bottom. And then we're also going to grab the quotient, which is the result of doing dividend divided by a divisor. And that's just going to be values at I. So for an example, if we focus on this right here, we'd have dividend equals A, divisor equals B, and then quotient equals 2. Now, what we want to say is to go from dividend to divisor, the weight is going to equal quotient. And then we have to handle the other direction, which is that to go from divisor to dividend, the weight is 1 divided by the quotient. And this is really all we need to do. The one thing is we have to make sure that graph at divisor is actually an object that we can insert a key into, and that graph at dividend is actually an object that we can insert divisor into. So what we'll do is we'll say dividend in graph is going to be graph.hasOwnProperty dividend. We'll do the same thing for divisor. So we'll divisor here, delete this. Okay. Then we can say if the dividend is not in our graph, we can say graph at dividend equals an object. Note that we're using an object because that way we can store weights instead of just storing an array. That would make it harder to store weights. And the weights, to be clear, are these values here. So to get from dividend to divisor, the weight is quotient. That's how we're structuring this. And then we'll do our other direction, which is if divisor is not in graph, set graph of divisor to also be an object. And that should allow us to construct our graph here. Now we need to get our query results. That's what we want to return. So we'll have an array called query results. We're going to iterate over each query. I'm thinking if we need indices or not. I don't know why it's indenting like this. Okay, whatever. I don't think we need indices. If we do, then we can come back and refactor this. But for each query, we're going to do some work, and then we're going to return query results in the end. Okay, now what are we going to do to the query? Well, we're going to have a dividend and a divisor, which is our query. First thing we're going to say is if one of these is not in our graph, then we just should stop. Like if we have x, we cannot even compute anything. We don't know what x is. So we can say if we'll have dividend. Actually, you know what? We can you reuse these from here? So we'll say if dividend is not in the graph or divisor is not in the graph, then we can just push -1. We know that it's not even possible to make this combination, and we're going to continue on to the next query. Now we don't want to use -1 as a magic number, so instead we'll have a constant cannot determine answer, which is -1. And here we will push cannot determine answer instead of -1. Okay, now at this point we will compute the quotient. So we'll have some function that magically does this for us. So we'll say quotient equals compute quotient. Let's say it takes the graph, it takes the dividend, it takes the divisor, and I think there's one more piece of data that we can add in a second. But this quotient might say, hey, I actually couldn't even determine an answer. So in that case, we would want to push -1. But I think we actually don't need to handle that separately. I think we can just do query results.push quotient. If it's -1, then we're going to push -1 from cannot determine answer. Otherwise, we're going to push the actual quotient. So this should be fine. Now, the other thing we're going to need is we're going to need a visited set because we could potentially have cycles, right? This is an undirected graph, or it's not an undirected graph, but every pair of nodes that has an edge, that edge goes both directions. You can go from A to B and B to A. So theoretically, if we're looking for a path, we could just go from A to B to A to B to A to B, and just keep doing that forever, which doesn't make sense. That's not really a useful path. So we're going to have a visited setup here, and we're going to note when we've already visited something. And if we've already visited something in our current path, then we can go ahead and stop processing it. Okay, yeah, that makes sense. And we'll see that in action shortly. All right, so we'll have our compute quotient function. This is going to be a recursive function that's going to execute our DFS and tell us the answer to dividend divided by divisor. So we will have our 3 steps: our base cases, our process node, and our recurse on neighbors. Now let's see here. How do we want to do this? So, okay, in our process node, we always have to mark the current node as visited. So we're going to say, or maybe dividend, is that what we want to call it? Yeah, that's okay. Dividend is kind of like our current node in many other problems we've seen. So we're going to add our visited, or our dividend to the visited. Then we're going to get our neighbors. So our neighbors is going to be graph at dividend, because remember dividend is our current node. We'll delete this here. But remember that when we use this way of storing weighted graphs, we use objects here instead of arrays. So to get the neighbors, we actually need to get the keys of the object that is graph at dividend. Then we can go through each neighbor of our neighbors, and we can say, what do we want to do? Well, remember, we want to assume this function works magically. So we're going to say, if we did compute quotient with graph, with neighbor, the same divisor, which is kind of a target, and then visited, we're going to get that result. So we're going to say quotient equals that result. Or we'll say, let's see, we can say neighbor over divisor. So let me show the math that I'm going to try to do here. So what we know is dividend divided by neighbor, right? If something is a neighbor, we know the kind of weight between them. So dividend divided by neighbor. I'm going to take this and I'm going to multiply it by neighbor over divisor. Because remember, we kind of magically assume our recursive function can compute this for us. We pass it the neighbor, we tell it same divisor, it'll give us this answer. And if we multiply that by this quantity right here, we're going to get dividend over divisor, which is exactly what we want to return with this function. So we're going to do that. So if we come back here, neighbor over divisor is our recursive call. And then we can also do, let's see, dividend over neighbor equals graph at dividend at neighbor. Remember, here we're saying to go from dividend to divisor, the weight is quotient. So to go from dividend to neighbor, the weight is going to be stored here. Then we can actually, yeah, this looks right. Then we can get, let's see, we can do dividend over divisor, which is what the goal is to compute right here, is going to be the product of these two. So we're going to do dividend over neighbor times neighbor over divisor. And remember, this is like dividend divided by neighbor times neighbor divided by divisor is equal to dividend over divisor. That's the math I just wrote out. And here, if we find this answer, we can return it. So we'll say return dividend over divisor right here. Now, there are two details that we've missed that I want to add right now, which is that sometimes this compute quotient will say, hey, it's not possible to compute this quotient. We need to stop. So we need to handle this case. What if neighbor over divisor says, I can't even determine that? Well, we don't need to return yet, because maybe there's a different neighbor who actually can find the answer. But we know the current neighbor is not useful, so we should skip it. Okay, so this loop should be working now. Now, there is one thing that we need to handle, which is sometimes we'll never get here. We'll never get to actually return an answer, because all of the neighbors don't have a path. They're all invalid neighbors or something. Or maybe there just are no neighbors. So we need to handle our default return value, which should be, hey, there was no answer. We want to return -1 to say, like, from the current dividend to the divisor, there is no path. Okay, conceptually, I think this should be most of what goes on in these steps. Now we need to handle the base cases. So there's a couple of things we want to handle. First of all, we know that whenever we have a visited set, we should have a base case for it. So if we've already visited our dividend, what do we want to do? Well, that means we're in a cycle, right? We went from A to B to back to A. So we don't even want to consider this path. We want to say, hey, stop this. Don't even look down this direction. So we're going to say cannot determine an answer, at least not from the direction that we're looking at. And that's just going to mean it'll get continued over here. The other option is, how do we actually succeed? How do we say I've found my answer? Well, here we're going to start at A. We're going to make a recursive call to B. Let's see if we can actually model this. So we're going to be at A. We're going to make a call to B. So we're going to say, let's see, we'll call our function f. So we're doing f of A comma C. And what we're going to say here is, okay, this is going to equal 2 times f of B comma C, right? Because the weight right here is 2. We come to here, we're trying to figure out f of B comma C. And we decide this is going to equal 3 times f of C comma C. And that's because this weight right here is 3. F of C comma C, well, what do we want that to be? Well, we know that f of B comma C should equal 3, right? We know that B divided by C is 3. So this should be, let's write that in a different color, so we can say it should be 3, and it's going to equal 3 times something. Well, then that something must equal 1. And that something is actually f of C comma C, so f of C comma C should equal 1. If f of C comma C equals 1, then f of B comma C right here is equal to 3 times 1, which is 3, which is what we want. If f of b comma c equals 3, then we can come back over here. We can say f of a comma c equals 2 times 3, which means f of a comma c equals 6, which means a over c equals 6, which is exactly the output that we desire. So the key is that the base case right here is when we have something over itself, 1 should be the output, which makes sense. If you have like c over c, then that equals 1. As long as we actually know what c is, right? If it's like x in this example, well, what is x? We don't know. Okay, so our base case here is going to be if dividend is equal to divisor, we're going to return 1 and say, okay, this is something over itself. The answer there is just 1. Okay, now because we assume that our compute quotient function works magically when we make our recursive calls, this should be our desired behavior now that we have handled the base cases. So I think we can go ahead and run this and see if there's anything that I missed. So if we run here, looks like we're getting an incorrect answer. Why is that? We're doing -1 here. Okay. Interesting. So we're saying to get from B to C, the answer is -1. So first of all, I'm going to print our graph. Just make sure our graph looks good. So from B, we can get to A with 0.5. Okay, yeah, so this looks good to me, graph-wise. B can get to A with 0.5, and it can get to C with 3. I think that's right, 1.5 and 3. Yeah, that graph looks correct. Or at least that part does look correct. This looks correct as well. Okay. So when we're trying to compute B over A, what is happening? We're saying B over A, neither of these should be triggered, so we're going to compute a quotient with B. Okay. The key here is that we need to delete the current node from our visited, I believe. Let's confirm that that is the actual issue. I think .delete is the way we do this. If that is correct, then I'm going to explain why that is what we need to do. Yes, okay, it looks like it fixes that. Does not fix this. So here we should be returning 1, but we're returning -1. Why is that? That's interesting that we're returning -1. Why would we return -1? I wonder if it is the case that we also need to be deleting here. Yes, okay, that is the case. Yeah, that makes sense. Then, okay. So the issue is this. Let me see how we can draw this out here. Oops. Zoomed out a bit. Okay. So, interesting. Okay, this is a small graph, which makes it a little bit harder to explain the concept here. First of all, the key is what we need to be doing is backtracking. Okay, I guess one way to view this is imagine we need to get to E over here. You know what? Okay, imagine we need to get to F. But maybe we have a route that looks like... Okay, this is kind of a bit difficult to explain, but I'll try to explain it here. The key is that if we start at A, then we go to B, then we go to C, and we mark it as visited. But this leads to a dead end, so we say, all right, we don't need to continue anymore. That's it, we can stop right now. Then when we go back here, when we go to E, imagine that E had a path to C. Well, it would try, if it tried to go to C, it would say, hey, this is already visited, I don't want to consider it. But maybe now there kind of is a path from E to C, and we should consider that route. So that's the key. We need to delete C when we're finished examining C. Delete C from the visited, to be precise, to backtrack and say, hey, maybe other paths can consider C, but I cannot. So that solution does work. I thought I remember a way to do this without backtracking. So I think it might be worth it to glance at the collect solution, which I had open here. Let's see if there's something missing. Yeah, it does look like I'm not doing backtracking here. So let's try to see what the difference is. Okay. The other way you can handle this is if you don't want to have the visited from previous query results, then we can just have a new visited every time. That makes sense. So we can do that too. Okay, I think I understand what's going on. Let's just make sure that works. Yes, okay. So I think my explanation of it was kind of slightly off the mark. The general idea of backtracking is this, but the key was that we're evaluating multiple queries here. And so maybe first we look at A over C, and then later we look at, I don't know, A over A. Okay, yes, this is definitely what was happening. This is an actual example, like from our real input. When we get here, we find the answer to be 6, but we mark, all right, our visited contains A, B, and C. When we get to this computation here, the first thing we do is we come here, we say, is it visited? If so, return -1. And A is already visited, so we return -1. The key is that every time we are looking at a different query, we want a new visited set that we can work with. The reason the answer from before worked is because when we backtrack, by deleting from the visited set, every time we finish a query, oops, I don't know why it's doing that. Every time we finish a query, our visited set is empty. That's kind of how the backtracking works, because every time we added here, we made sure to delete before we returned. So in the end, when compute quotient is done, specifically when this invocation of compute quotient is done, visited is empty again, which is why we did not need to create a new visited set every time. So either option works. You can do the backtracking and have one visited set, or you can just throw away the visited set after you use it and make a new one at the next iteration. But both options work and allow us to solve this problem. All right, that's all for this video, and thank you for watching.